Alright, so today we are starting our discussion with a look at the bigebra of associated, I guess just right, associated to a formal group. I know we studied bigebras a fair bit before with our discussive Lie algebras and Bourbaki. So I think this might be connected to that, but it is different. I've checked. I didn't recognize a lot of what I saw. So first off, we're going to I don't need to number this. I'm going to let G be a Lie group. This is the convergence case in an analogy to the formal case. I'm stumbling over my words. So G is a Lie group. H, its local ring at the identity. M, its maximal ideal. I guess of H, with maximal ideal M and completion H, and this is a completion with respect to the topology defined by M and U, the point distribution. You can define it to be on H or H hat, it doesn't matter. Then we have a diagonal map. We saw this last time. We have a diagonal map delta from U into U tensor U. And we now define a multiplication theta from U tensor U onto U by the group law on G, which we are going to write as a map phi from G times G to G. Then we can define a map sigma from H underline of E, which we're going to define in a second, to H underline of E comma E by sending a function f Sorry, that's a real messy arrow. F to F composed on phi with H underscore of E being H and H underscore E comma E being the local ring at E comma E on G times G. From our map sigma, we get a map sigma hat from H hat to H hat on E comma E, which is the completion of the tensor product of the completion of H with the completion of H. So by dualizing sigma, we get the desired theta from U tensor U into U. You'll see in the formal discussion that U is an associative algebra under theta, with our unit being the Dirac distribution. So now we are in the formal case. We are going to use our same setup with H underline being the ring of formal power series over Y1 through Yn, and Z1 through Zn, and we let F in H underline to the N be a formal group law in N variables over K. Recall that we showed that in this case H underline is the completion of the tensor of H and H, and we're going to let M hat be M tensor hat H plus H hat tensor M. Then, since F is without constant term, given an F and H, we may form the composite map of F with our group law, which is then going to be an H underline. We then let sigma denote the map from H to H underline as this sending F to F on our group law, with then sigma of MR being in M hat of R. So sigma is continuous with respect to the relevant topologies on our two M's. And of course that means sigma induces a map theta from U times U onto U by dualizing. This brings us to our first lemma. Did I start my timer? I did, okay. So, our lemma states that theta makes U an associative algebra with unit being the Dirac delta distribution. And the proof: we're going to consider H underline being the formal power series ring over Y and Z, and H hat, I'm using hat because they write in bold, which I cannot do with this setup, being of K, the power series ring over Y, Z, and additional W, with W being in N variables. We shall let delta alpha sub Y, delta beta sub Z, and delta gamma sub W be the duals of the monomials Y alpha, Z beta, and W gamma respectively. Now we prove the associative law. So we're going to let gamma alpha tensor gamma beta tensor gamma delta gamma a quote-unquote typical basis element of U tensor U and F, B, and H. And then we got some very messy formulas. Well, theta of delta alpha on theta of delta beta and delta gamma on some F is then going to be delta alpha Y, delta beta Z, delta gamma W on F of Y, F of Z, and W. So essentially the idea here is that we translate this non-associative, if it's non-associative, it translates over from one to the other directly. And we likewise have the other case where we do alpha and beta first in the theta, and then with delta of gamma acting on some F, giving us the same, that's supposed to be a Y, not a gamma, Z beta, W gamma of F on F of Y and Z and W. So theta is associative from F. Now we want to show that the Dirac delta, which we write confusingly as an epsilon here, is a unit. So we're going to let delta alpha be in U and F in H. Then theta of epsilon delta to the alpha on F is epsilon sub Y with delta Z to the alpha F on F of Y comma Z which is delta sub Z to the alpha of F on, that's going to make, of course, our Y 0 and Z, because it's the Dirac delta at Y. And this itself is then equal to delta Z sub to the alpha of F of Z. And so theta of epsilon and delta to the alpha is delta to the alpha. So epsilon is a left unit. Being a right unit similarly. Yeah, so from this we have our second lemma, which states that the diagonal map delta from U to U tensor U is an algebra homomorphism. And we need, so for proof, we need a diagram to commute, which is a very complicated one. So we have U tensor U tensored with itself. We can send this by alpha, which we're going to define in a sec. Alpha is the braiding map for the middle two U's. I'll write down at the bottom in a second. We can map to this from U tensor U by delta tensor delta, theta to be U, to be delta of U tensor U, and we can go down on this side with theta tensor theta. With alpha of x tensor y tensor z tensor w, as I said, being the braiding map, so it just swaps these two elements in the middle. I need this to commute. Since all modules here are free, we can show the dualized diagram, which went right, and we're going to show this is commutative, where this is going to be H completed as tensor, and yeah, so here we're replacing the U's with H's. That's going to be everywhere actually. Here this map's going to go the opposite direction. It's going to be alpha prime. It's going to be H hat tensor H hat tensor H. And we have here this map's going to go down now by mu hat tensor mu to H hat tensor H. We have an H in the middle here. We have H hat tensor H. This map is going up by sigma hat tensor sigma. This one's going backwards by sigma hat. Oh, this H actually is going to be complete on its own. This is going to be mu. Need this to commute. Now, since all maps here are continuous with respect to the relevant topologies, we check commutativity on elements of H hat tensor H as, say, F tensor G, for F and G and H. But we know that sigma hat of mu of F tensor G, because if you look at this map, that the kind of like source of the arrows is here is our H hat tensor H on the right, and you can go up and around and down, or just straight across back to the other copy of H hat tensor H. So here we're going straight across, and then we're going to try to just wrangle this into our other form. So this is sigma hat of F dot product with G, which is the same as F G composed with F, which we can then distribute along this product. Which is mu hat tensor mu on alpha prime of f on f tensor g on f, which is mu hat tensor mu on alpha prime on sigma hat tensor sigma on f tensor g. I thought I missed a bracket somewhere, but they just messed up, so. And we are done. Now U with our diagonal map, delta from U to U tensor U, and theta from U tensor U to U, this multiplication, is called the bigebra associated to the formal group F. We write theta uv as u star v. I'll put tails on the u's, otherwise it's going to be illegible. And u bracket v star. The star bracket is going to be u star v minus v star u. Alright. And then we're just going to keep on going here. I'm running out of water. I might have to pause to go grab some. So, lemma. For all alpha and beta, we can think of delta alpha times delta beta to be alpha plus beta, choose alpha, of theta to the alpha plus beta, plus some error term, alpha beta, with the error term being a linear combination of delta gamma with the size of gamma being between 0 and the size of alpha plus beta. Alright, so we now need, if gamma is greater than or equal to alpha plus beta, then delta alpha star delta beta, and alpha plus beta, choose alpha on theta to the alpha plus beta, agree on x to the gamma, and e sub alpha beta is going to vanish on k. And how do we do this? We note first off that x gamma on f of y comma z is f of y and z to the gamma, which is y plus z to the gamma plus our error term where d0 is at least the size of gamma, and y plus z to the gamma is over lambda and mu being gamma. Gamma, choose lambda times y to the gamma, z to the mu. Now, since we know that delta to the alpha times delta to the beta of x to the gamma is delta sub y to the alpha times delta sub z to the beta of x to the gamma on f of y and z. Sorry, one second. I will pause here really quick. I'm just going to go grab some water. I'll be right back. I probably won't even edit this out because it's going to be just a few seconds, so ideally. But yeah, I don't know why I didn't prep this ahead of time, but thankfully where we keep our water is right next to where I'm sitting, so I can just do this real quick. And I'll just set the jug on my table here right away. I'm stalling for time here a little bit. It'll just take me a couple seconds here to get everything back in place. You can hear there'll be a lot of loud noises, very uncomfortable for you. I'm sorry about that. The jug in the way, I'll need to put that there. Alright, sorry about that. So since we have this identity, we can get delta to the alpha on delta to the beta on x. Gamma is going to be alpha plus beta, choose alpha if, if gamma is equal to alpha plus beta and is going to be 0 otherwise. So I'm going to write that with the, I don't know what the delta that takes 2 arguments is called, but I like it better than a piecewise function. And of course we can also write this to be the delta of alpha plus beta on x to the gamma. And this gives our assertion of the action of delta alpha is delta beta, and alpha plus beta, choose alpha times delta to the alpha plus beta in x to gamma if gamma is bigger than alpha plus beta. And both elements, of course, give 1 on x naught when alpha plus beta equals 0, and they give 0 otherwise. So E sub a alpha comma beta always vanishes on K. Now we're going to let G be the Lie algebra of the formal group F, which will, we know, then have underlying vector space being our k to the n. We're also going to let d to the I be the ith standard basis vector of k to the n, and define C from G to U by C of dI being delta to the delta sub I. Then by definition, C is a linear isomorphism of G onto the set U of U and U such that U of U vanishes on k and m squared, as we expected from our convergent case, the not formal case. Alright, so got another lemma. So for all x and y in G and f in H being a linear function, C of the bracket of x and y on f is f on b of x and y minus b of y and x, which is by definition f of the bracket of x and y. And now since both sides are trilinear in x, y, and f, we can reduce down to a case where we have everything being a basis element. So x is di, y is dj, f being x of k. Then both sides, sorry about that, reduce down to our structure constant, gamma I j to the k on d1 through dn, and we are done. There's a lot of stuff here to prove, but we'll keep going for a little longer. Theorem, C is a Lie algebra homomorphism as C of the bracket of x and y being the bracket of cx and cy on our star case. Now we know that C of x and y vanishes on k and m squared, as does cx and cy on our star bracket. Alright, new page, so hence we can show they agree on a set of coset representatives of m over m squared, e.g. the linear functions. So we're going to let f and h be linear. Then Cx on Cy with our star bracket on f is going to be Cx tensor Cy minus Cy tensor Px right in our bracket with our tensors. Then apply the f on our formal group law of our indeterminates x and y, not the same as the ones indexing as the arguments inside the bracket, which we can write this term out on the right more explicitly. As f on x, f times x plus f on b, x, and y, plus some higher order stuff, who cares, which is f of b of x and y minus b of y and x. And so we get the equality we want from our last lemma. Because we saw that this is equal to c of xy on f. And it looks like we're still not actually up to time yet, so we'll keep going. Now going forward, we assume that K is a rational algebra, and we let the map C, we extend our map C from our Lie algebra to be the map induced by our map C from G to U. There's just a natural extension to the universal algebra enveloping G. So we're just going to kind of push it over there without too much thought. We're just a theorem where C from U of G to U is actually a bialgebra morphism. Alright, so now we have filtrations on the universal enveloping algebra of G and on U. With C being compatible and the filtration on U of G, or alternatively just U, is separated exhaustive and makes U of G, or alternatively U, discrete. So we can just show that the grade of C is bijective, to show that C is bijective. Now, by Poincare Birkhoff-Witt theorem, UG is a free K module with a basis d alpha being d1 alpha 1 through dn alpha n. Since K is a rational algebra, U is a free K module with a basis, we're going to write it as D underlined to the alpha, which is going to be 1 over alpha factorial times our delta of alpha. As by our previous lemma, psi and alpha, psi of d alpha and underscore of d alpha agree in the grade of U. The grade of psi is bijective, so that psi is bijective. Now we know psi is an algebra homomorphism, so we are left to show that we want it to be a bialgebra morphism. So we have this map from UG, we have delta sending it to, let me write this out better, to UG tensor UG being the delta map. We have psi sending U of G to U, which delta then sends to U tensor U. And so this corresponds to doing psi twice. Now we know that both deltas are algebra homomorphisms, and that for U in G as a subset of UG, psi on psi of delta U, delta of U, is just psi of U tensor 1 plus 1 tensor psi of U, which is just our delta on psi of U. Since G generates U of G, psi on delta is delta on psi on all of UG. And we are done, and I believe we are going to call it there for a video for today. Thank you for watching. Next time, it's literally just more of this. There's like, I don't know why this section is so long, but there's just a bunch more lemmas and stuff we gotta get through. So we will be getting through it tomorrow. Yeah, thanks for watching.